Hi. We're given a list of heights of buildings, and imagine that we're standing in front of that list and looking onto these buildings. Then we cannot see a lower building that's behind a taller building, but we can see a taller building behind a lower building. So just needing to see a little piece of a building in order to count it as being seen, how many buildings can we see? Let's have some test data. So here we have two buildings that have the same height. That means that the second one is entirely obscured by the first one. And here's one that's lower, which means you can't see that either. Then there's a higher one. That one we can see. And again, a lower one. And that's obscured behind both this number 10 and the 5s over here. So certainly we can't see that. Then there's a 15, which is bigger than the 10. And that's our third building we can see. And the 10 is obscured behind the 15. But we can do this by hand. We want to write an APL function that does this. And let's start by defining a function. So this is an anonymous lambda, and we're putting the test case on the right, referring to it with omega, which is the rightmost letter in the Greek alphabet, and therefore is indicating or is a symbol for the right argument in defins or lambdas, if you want. Okay, now we can start computing. And what we want to do here is we want to traverse from the left to the right and all the time looking at how high a building have we seen so far. And what we can do is it's called a scan, using this backslash. It's a cumulative reduction, and in this case we're using the maximum function. So maximum of 5 and 5 is 5, maximum of 5 and 2 is 5, and then we can see that, so here we're getting a 5, and then with the 10, we go up to 10, and the 10 continues until rolling over the 3, because we're doing maximum, until we get the 15. So let's try that. And now, all we need to do is to see how many different numbers are there, because we'll never get a lower number after a higher number, but we can get some of the same. We're not interested in these are the same. We only want to count the first one of each. And a simple way to do that is simply taking the unique of that. So these are the heights of the buildings, but the problem statement is to count how many there are. So this tally mark counts how many there are, and there are 3. So let's call this F. This is a very short, neat solution to the problem. There are other ways that we can solve it. Let's start again with this cumulative maximum. And this time, we're going to look at the mathematical relationship between these numbers. So we're interested in whenever we go from one building height, a plateau like this, to the next one. We want to find the places where we're looking at consecutive adjacent elements, we have an increase. And we can do that by comparing pairs, 5, 5, 5, 5, 5, 10, 10, 10, and so on. So we want to reduce using less than. So reduction is the forward slash, and the cumulative reduction is the backward slash, backslash. But we don't want to reduce over the whole thing. We only want to reduce over sub arrays of length 2. So that's what the 2 on the left means. And we can see that these numbers then correspond to the spaces in between. So 5 is not less than 5, 5 is not less than 5, but yes, 5 is less than 10. There's but one problem, that since we're looking at the change here, then we're missing the we're missing 1, because there's only 1 1 for the change from this size to this size, and 1 1 from this size to this size. That's 1 less than what we have. So we could solve this in a couple different ways, but a very simple way is to add a 0 in front. Note that we cannot just add one, because if we try to use an empty list of buildings and we added one, then if it wasn't for giving issues with the pairwise reduction, we would be adding one to, because there would be no buildings, and then we'd add one. We say there is one building, but there aren't any. But if we put a 0 in front, then we will get an increase from 0 to 5. The problem statement says that these will be positive height buildings. It makes sense. So let's put this in again, and then we can see that we get a 1 at the beginning. And all we need to know now is how many ones are there, and we can do that by summation. So this is a plus reduction. So we're using a plus reduction, a pairwise less than reduction, and a cumulative maximum reduction. And this gives us the 3 as well. Let's call this G. Now, if we think about what is the performance going to be of these, then F has some pretty bad issues. We're using unique here, even though we know a lot already about what this array looks like. We know that it's a non-decreasing list of numbers, and unique will have to, it doesn't know this property. So it will have to compare all the different numbers that are in the list, which if it was a big city, could be a lot of numbers. And it might do some hashing and things, but it's still not going to be very efficient, because it doesn't know that all we need to do is look at where the numbers increase. And then it produces these numbers, which we actually don't need anyway. So even that will take up memory, just for a new array containing all the unique numbers, only for us to then count it. So we're not actually interested in the result of the unique. We just need it for the counting. So that's really inefficient. Whereas G is much more efficient. We start off the same way. So of course that's the same thing. We'll get back to the 0 comma for a moment, is concatenation. Then we switch to a Boolean array. And as soon as we do that, APL is clever enough to compress this into using 1 bit per element. So that means we're now down to an eighth of the memory used to represent all the data we need to compute on. If we have 1 byte integers in the height, if we have even higher buildings with multiple byte integers internally, then it's going to be even more extreme difference. It could be a factor 16 or 32. And then summation of this Boolean is going to be really fast, because the processor has instructions on counting how many ones there are, how many bits that are set in a byte, and we can do this in enormous chunks as well. We don't care about the individual bytes. We just want how many unbits are there in the entire memory that we give it. So that's going to be really fast. However, there is one issue, and that is the 0 concatenation here. This is our original data that we get in, and if we concatenate a 0 on the left, that actually means that we have to rewrite everything in memory, because the numbers are stored in their order, and we have a pocket. So even if there wasn't the issue of preserving this array, which we would anyway, we have to rewrite an array of almost the same size to one element more, rather than doing the computation directly on the data as given. So this is going to be a quite expensive operation just in memory write time. And in today's computers, very often the actual highest cost is memory read and write. The processors are now so fast and so smart that they'll just sit idle waiting for us to give them work to do all the time. And many operations just happen at memory throughput time. This is the real bottleneck, and we want to avoid memory rewrites like this. So how can we code around this? We can make a copy of G where we want to avoid this. Remember I said before that there's an issue if we have an empty list where we can't just add one that becomes wrong. But let's ignore that case for a moment. So here we know that we are off by 1. We're missing the count of 1, which is the initial going from 0 to the first building that you can see. So we add that back here, and this gives us the wrong result if the argument is empty. But we can do the check if the argument is empty. So let's make two statements. This is the diamond is a statement separator. And then we have what we call a guard. It's like an early out condition. And we're going to take this is a short format of writing the empty numeric list. And if that matches the argument, then we know that there are 0, right? We cannot see any buildings if there aren't any buildings to see. So this is a really quick check. We're not comparing any data. We're just immediately looking, are these the same? We don't even, yeah, I think even internally it's represented as some constant that's always there. But even if it wasn't, we're talking about looking at the data type of the array, that they're both numeric, and looking at the shape of the array, and they're the same shape. So we're done. That's there because there's no actual concept to compare. So this is a really quick check. Of course, it does add some overhead, and it does add a branch point where a branch particular could fail, but it's going to be dwarfed by the actual computation that happens in the general case. And of course, here we are saving ourselves even one comparison everywhere, and we get a single number, and then we're adding 1, which is really cheap, obviously, as well. Okay, so let's see if we can actually see the difference in performance. We have a tool called CMPX, or compare execution. We'll copy it in from the defense workspace. And then let's generate a cityscape with a whole bunch of numbers. Let's do 1,000 buildings, and then I'm going to randomize. So the first one is going to be a size 1 building, and the second one is going to be a size 1 or 2, and then the third one is 1 or 2 or 3. So the question mark roll, it takes a number and generates a random number between 1 and that number, and the iota generates a sequence from 1 to 1,000, in this, because we give it 1,000 on the right. And what this means is that in general, the buildings will become bigger and bigger. If we made them all the same, then pretty quickly we would not see anything more, very little likelihood of seeing it. So this ensures that we'll still, even towards the end, we'll still be seeing more buildings. Right, 1,000 random buildings, and then we write our expressions that we want to test. So we want f applied to s, and g applied to s, and h applied to s. And now that we wait a moment for it to run these expressions a whole bunch of times, and comparing them to each other. And we can see here that there's quite a significant difference in the performance between them. But also, the definitions are maybe getting more and more complex, and certainly longer. So sometimes you just have to weigh it between how neat you want the code and how performant you want it. You can't always have both. Thank you for watching.